Here, we're gonna, get down to some actual calculations with vectors, right? Okay, so if you wanted to write, we're going to talk about the different forms in which we could express vectors. So first, let's talk about the component form of a vector. This is a way to express your vector, okay? And suppose you're given the initial point of the vector in coordinates, and you're given the terminal point of the vector in coordinates, right? Initial point, terminal point. You can express the vector in coordinate form by, here's what you do. You subtract x2 minus x1. You subtract y2 minus y1. But then you have to put them in these brackets. So it's x2 minus x1, comma, y2 minus y1 bracket, all right? They've got to be in those brackets. So let's take a look at this one. It says find the component form of vector AB with initial point A and terminal point B. So all we have to do is say AB is, in brackets, 1 minus 1, comma, negative 3 minus 3. Oh, no. 3 minus negative 3. It's got to be B minus A. It's got to be, right? Order matters. 3 minus negative 3. So AB is equal to 0, 6. Now, let's see what that means. So first here, order matters, right?
Oh, that's so weird. I thought it was like terminal and then terminal and then what? No.
Oh, okay. All right. Okay, so let's see what this means. Boop. Okay. Let's plot A, right? A is 1 comma negative 3. B is 1 comma 3. And the vector goes from A to B, so it's in that direction. Okay? Now, what did my component form look like? It's 0 comma 6. So the first value there is the x. The second value there is the y. What the component form gives you is a route to go from the initial point to the final point. This is telling you to go from the initial point to go to the final point, you have to go 0 in the x direction and positive 6 in the y direction. Is that true? 0 in the x, positive 6 in the y. Tell me that's not cool. Right? It's so cool. It's kind of like slope, right? Except like it can never be undefined. Okay? So if it was 2 comma 3, let's say, you would go 2 in the positive x direction, 3 in the positive y direction. Now, since magnitude is represented by its length, right? How do we find the length of a segment? Distance formula. Okay? What is the distance formula? It's, here we go, x2 minus x1 squared plus y2 minus y1 squared, blah, 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 blah. But what did we just say? That a vector v in coordinate form, it's what? x2 minus x1, y2 minus y1, right? Now, suppose I could write that as a comma b. Can I do that? Of course I can, right? So now, if a is the first term in the component, b is the second term in the component, what else could I do to find the distance? Well, it's just the square root of a squared plus b squared, right? Okay, so then that's what we're talking about here. Okay, so let's find the magnitude of AB with initial point A, terminal point B. Yeah, it's the same vector. So AB in component form is 0 comma 6. So magnitude of AB is just 0 squared plus 6 squared, 6. Okay? Isn't that cool? I know. You don't see it yet, but you will. You will. Okay. Addition, subtraction, scalar multiplication. Addition and subtraction. Okay? If you want to add two vectors, this is vector A and this is vector B, right? You wanted to add them. You just add the first terms to each other, and then you add the second terms to each other. Okay, so check it out. Let's do this one, and then I'm going to show you something else. So take a look at this one. 2w plus y minus 4z, and you've got, all of those vectors there. So what's 2 times w? It's 2 times 2 negative 5 plus y minus 4 times z. Yeah, can I just combine them from now? So it's 4 and negative 10. And then it's minus 4 times z, negative 4, negative 16, right? So now if I add all these up, it'll be 4 plus 2 minus 4, minus 4. So that's how much?
4 plus 16.
Well, it's minus 4 times z. 4 times z is negative 4 and negative 16.
Oh.
Right? So you could. I mean, it's yeah. So how much is that going to be then? 10, comma what? 6. All right, and you could do the other one. I don't think we need to go through it again, do we? No.
They have this on our hours.
Yes, they do. Okay, let's go back to matrices for a minute. Suppose I have a row matrix A. It's a 1 by 2. And I have a row matrix B. It's also a 1 by 2. Okay, how do I add them? 2 plus 4. Right?
Oh, add them, sorry.
And 2. Right? So now what's the difference between that and the vectors that we just did? No difference. Because guess how else a vector could be presented? As a row matrix or a column matrix. Right? And a row matrix is just a vector sometimes. That's the power of them all. That right there is the power of them all. Right there. Okay. Now, let's talk about unit vectors. A unit vector is a vector with a magnitude of 1. All right, it's just a little arrow with a magnitude of 1. Consider vector v, right? Vector v is this entire thing here. Its unit vector is u. Here is u. All right? It has the exact same direction as v, but a magnitude of 2, right? So if I were to take out a ruler and measure v, it's 2.5 inches or centimeters or whatever. U is the same direction, it's just got a length of 1. So now, in order to make v into a unit vector, am I changing the direction? No. I'm just changing the distance, right? What can I do to this 2.5 in order to make it a 1? Divide by 2.5, divide by the magnitude. So, to find the unit vector u, given a vector v, I just realized if they're all bold, there is no difference between. That's on me. Okay, so to find the unit vector, you just divide the vector by its magnitude, right? So divide V by its magnitude. So let's find the unit vector here, the same direction as V. So first we need V magnitude. It's the square root of 16 plus 4. How much? 2 root 5? 2 root 5. Right? So U, vector U, is going to be 1 over 2 root 5 times 4 comma negative 2. So do we see how we're dividing by the unit vector, by the magnitude of V? Yes? So, okay, so here's what I'm doing. Yeah. So it's 4 comma negative 2 divided by 2 root 5. Well, we have to separate it now. So U is going to be 4 over 2 root 5, comma negative 2 over 2 root 5. That means vector U is going to be 2 over root 5, negative 1 over root 5. And you don't have to rationalize. Okay? Now, that has the exact same direction as V, but just a magnitude of 1. All right, questions? Right, so let's draw vector V. Vector V has x component of 4, y component of negative 2. So let's do this. X component of 4. So we're going to go positive 4. Is that positive 4 and negative 2? Is that right? So that's V. It didn't turn out right. Okay. So that's V right there. All right, now, how are we going to draw U? Okay, so now do this for me. What's 2 over root 5 in decimals? It didn't come out right. How much is it?
0.89.
What is? Look, it's 4. Sorry, one more time. What did you say? 2 over root 5?
No, it's 0.894.
894. And what about 1 over root 5? It's half of that. So how much is that?
Uh, 0.447.
Right. Okay. So this is okay, so now let's draw the unit vector U. I want to do it in green. All right, let's do the unit vector U. So it starts from the same place. It goes 0.894 to the right. So from here, 0.894 to the right. I'm estimating here. And then negative like 0.5 down. So right there. Right there. Okay, so that's how it looks. So now, so do you see the green one? That's the unit vector U. So it's just a tiny little vector. All it does is point you in the right direction. It doesn't give you a magnitude. It doesn't give you anything. So this is the little tiny unit vector U. And if I were to, do Pythagorean theorem on this, that diagonal side would have a length of 1. Okay? All right. Now, unit vectors are so important that if I have unit vectors in the horizontal direction only, right? So something like this, it's going to have a component 1, 0, right? Because you just go over 1 and up 0. So the horizontal unit vectors, they have a special name called I. And then the vertical unit vectors are J, and their component form is 0, 1. So now take a look. When you write I and J, when they're the unit vectors, I and J, they have a special notation. So it's I hat and J hat. Okay? That's the notation for a unit vector. Unit vector I hat, unit vector J hat. So take a look here. Each one of these light blue and red ones are unit vectors. So if I have a vector V right here, I can represent those by a series of tiny little unit vectors going up and going over. Okay? So that's what those unit vectors do. Okay. Another way to represent these terminal points. So let's write these. Let's write DE as a linear combination of vectors I, j. So here's what we're going to do. Let's write DE in component form. Right? What would that be? x2 minus x1, 2 plus 3. y2 minus y1. So the component form of DE is 5, 9. Is that right? That's the component form. Now, you could also write that as a combination of I's and J's. So that could also be written as 5I plus 9J. Okay, so that's a linear combination of I and J. Because depending on like the context and depending on like the field in which you're working, one is like, it makes more sense to write it in one way than another way. So what we're doing here is just getting you used to all the different types. Okay?
So is there like a special time or in which you should use these?
Not necessarily. It's just a matter of like,
what the directions to use?
Yeah, yeah. All right. So let's take a look at this. Okay, so suppose you know the magnitude of the vector and you know the angle that it makes with the positive x-axis. You know those two. Okay? Then you could decompose V into its horizontal and vertical components. Right? This is what we were doing yesterday, remember? So if I know V and if I know theta, then how could I write x? X is just V cosine theta. And y is just V sine theta. This isn't new, right? This is what we were doing yesterday here. Remember? X is always the magnitude cosine of the angle. Y is the magnitude sine of the angle. Right? So those you should just do like without even batting an eyelid. Okay? So, therefore, okay, if you have a vector V written as component form, okay, you can write it in component form using this. Okay, so the x component is V cosine theta and then V sine theta. So take a look at this one. Find the component form of the vector V with magnitude 7 and angle 60. So let's take a look at V. It's 7 cosine 60, 7 sine 60. Okay? And what, yeah, so what is the cosine of 60?
Oh, sorry.
Are you guys sure?
Yeah.
You're sure?
Yeah.
I'm sure too. 7 over 2. And what's sine of 60? It's root 3 over 2, right? So it's 7 root 3 over 2. And in decimals, how much would that be? 3.5 and?
6.6.
You sure? Looks like you're holding a calculator there. Mm-hmm.
Do you want us to leave it in fractions or in decimals, or don't specify?
6 point what? 6.06. All right. Decimals probably.
Okay.
I will specify them. So, or it could be 3.5i plus 6.06j. Okay.
So then y is negative and like whatever I.
Yes, exactly. All right. So let's find the direction angle of vector P. So vector P is 2 comma 9, right? So let's just draw that. I'm going to go up by 2's here. 2, 4, 6, 8, 10. So 9 is over there, and then 1 and 2. So that's P, right? How would you find this angle right here? You know that this is a length of 2, and you know that this is a length of 9. So how would you find that angle? Tangent, right? So tangent of theta is equal to 9 over 2. Theta is inverse tangent of 9 over 2. Right? And how much do you guys think? $77.5 sounds good to me. Okay. All right, let's do one more. A quarterback running forward at 5 meters per second throws a football with a velocity of 25 meters per second at an angle of 40 degrees. What is the resultant speed and direction of the pass? So here we go. Here now, we're going to be able to solve a problem like this explicitly using like math, right? Like our calculations. Okay, so we want the resultant speed and direction of the pass, right? How many vectors are at play here? How many vectors? We have one vector, the quarterback, he's moving forward 5 meters per second. So that's him. So we have 2. So that's one guy. So this is the quarterback Q. Okay? And then I have a second one. He throws the football with a velocity of 25 meters per second at an angle of 40 degrees. Where am I going to draw that second vector? I'm going to draw it at the end of the first one. So right here, okay, it's got to be an angle of 40 degrees. So almost like that. All right. And it's going to be a little bit longer, right? Well, 5 times longer. You don't have to do it exactly, like precisely. So this is what? Let's call this vector V. Okay? Now, what are the components of vector Q? Is there a horizontal, a vertical, or both in vector Q? The guy's running horizontally, right? So vector Q, The components are 5, 0. Is that right? What about vector v? It's got a magnitude of 25. So what is its x component? 25. Is x cosine or sine? Cosine. So it's 25 cosine 40. And then the y component is 25 sine of 40. What I need is this. This is q plus v. Okay? Oh, number 9, I didn't give you a... okay. I didn't give you the problem for number 9. All right, so here's what we're going to do. We want the resultant speed. Okay, this is magnitude. And the direction, that's the angle. All right, so that's what we need. Okay, so what is q plus v? Q plus v, right? How do we add them? We just add those vectors. So it's 25 cosine 40 plus 5, and then 25 sine 40 plus 0. So how much?
First one is 24.15.
24.15, and let's go to 2 decimal places. 16.07. All right, so this is the component form of the resultant vector. Now, for magnitude, what do I have to do? That's q plus v, magnitude. I'm going to take the square root of 24.15 squared, 16.07 squared. Right? So how much? Yes? 29.008. So 29.01, how much? Meters per second. Okay. Now, what about the direction? This is the inverse tangent always of y over x. So this is the inverse tangent, 16.07 over 24.15 in degrees. Okay? So inverse tangent 16.07 over 24.15.
33.61.
How much? 33.6 degrees is good enough. Okay? All right? Okay, so this next one, I'll do this one tomorrow. It goes with number 61. So do the homework until 53. I was supposed to give you, I just wrote the directions, but not the problem. So we'll do this one tomorrow.